Imagine gazing up at the night sky, trying to comprehend the sheer, almost unimaginable scale of our own Milky Way galaxy. It's truly vast. But what's maybe even more compelling are the tiny, subtle changes happening within that cosmic tapestry. Changes that can actually reveal some of the universe's, well, most profound secrets. Today, we're diving deep into exactly that. How the European Space Agency's extraordinary Gaia satellite is revolutionizing our understanding of what are called variable stars.
Mhm.
And what's truly astonishing is that, yes, you might actually be able to get involved in these cosmic breakthroughs. How exactly does that work, that everyday people can contribute to such cutting edge astronomy? This deep dive is all based on a recent research paper discussing the very latest Gaia data releases and the exciting intersection of cutting edge astronomy and citizen science. Our mission today is really to show how humanity is sifting through billions, literally billions, of data points to find surprising insights about the universe, and how human ingenuity and collaboration are still absolutely essential, even in this age of big data. Just to give you some context, before Gaia even entered the scene, we knew about approximately 150,000 variable stars. So, what kind of leap did we see with the first data releases?
Oh, it's an unprecedented transformation. But maybe let's set the galactic stage first.
Good idea.
Okay, so a variable star, in simple terms, is just a star that changes its brightness over time.
Hmm.
Think of it like a cosmic lighthouse with maybe a built-in dimmer switch. Some flicker rapidly, some pulsate over days or months. And Gaia, the European Space Agency satellite, is essentially a celestial cartographer.
Hmm.
It's meticulously mapping the positions, distances, and motions of nearly 2 billion stars in our galaxy.
It's just
Yeah.
2 billion.
Yep. And these twinkling stars aren't just cosmic curiosities, they're actually foundational to measuring the universe. By understanding their intrinsic brightness, we can finally map distances across the galaxy with unprecedented precision, decode how stars evolve, and even pinpoint the faintest whisper of an exoplanet as it briefly dims its host star. They truly are cosmic tape measures.
Cosmic tape measures. I like that. So the first big public data release, DR2, that came out in April 2018, it was based on observations taken between, July 2014 and May 2016?
That's right.
What was the most unexpected finding, or maybe the biggest immediate impact of that initial wave of data?
I'd say the immediate impact was just the sheer scale discovery. DR2 classified an astonishing 550,737 sources as variable.
Wow, okay.
Yeah, that's already more than triple the number of variable stars known before Gaia. It completely reshaped our catalogs. It included over 228,000 RR Lyrae stars and over 11,000 Cephides. And these aren't just any pulsating stars. Their unique pulsation periods directly correlate with their true brightness, making them invaluable standard candles for accurately measuring immense cosmic distances.
Standard candles, right?
Exactly. We also saw over 150,000 long-period variables and nearly 148,000 stars showing rotational modulation, where their brightness changes as they spin due to features on their surface, star spots, that kind of thing.
That's an astounding jump already. Over 500,000 just like that. But if you thought DR2 was a huge leap, Gaia Data Release 3, or DR3, which dropped in June 2022, sounds like it was a truly revolutionary moment. It covered an extended observation period, right, from July 2014 all the way to May 2017, giving us a full 34 months of data.
And the numbers are truly staggering. I mean, really mind-boggling. Out of the 1.8 billion sources in DR3, over 10.5 million were identified as variable.
10.5 million.
10.5 million.
Wow.
That's 9.5 million stars. And remarkably, about 1 million galaxies and quasars, too. Gaia collected time series data in multiple colors of light, the photometric bands G, GBP, and GRP, and for some, even radial velocity time series, showing how they move towards or away from us. These classified variables span an enormous range, from stars barely flickering by a tiny fraction of their brightness, just a few millimagnitudes, to those dramatically dimming by several magnitudes. It covers a vast spectrum of stellar activity visible to Gaia's precise gaze.
So way beyond just simple pulsations.
Oh, absolutely. The true revelation here isn't just the sheer quantity, but the astounding complexity Gaia has unveiled. We're not just finding more variable stars, we're discovering entirely new families of stellar behavior. After sophisticated period searches and time series modeling, automated systems assign these variables to 24 different classes. These include everything from Cepheid stars and Cephides, crucial for cosmic distances, to cataclysmic variables. Those are exploding binary systems. Eclipsing binaries, stars with exoplanets transiting, and even young stellar objects still forming in the galaxy. It's a whole zoo.
24 classes.
Yep, and just to give you a sense of this paradigm shift compared to DR2, long period variables, for example, jump from about 150,000 in DR2 to over 2.3 million in DR3.
Oh.
Yeah, and the Scuti and SXV stars, from about 8,800 to an astounding 7.4 million.
7 million. That's
Okay.
incredible.
It is. Plus, DR3 revealed entirely new categories in massive numbers, nearly 2 million solar-like stars that show variability similar to our own sun. Over 65,000 ellipsoidal variables where stars are distorted by a close companion, and even 214 confirmed exoplanet transits found directly in the variability data, which, raises an important question. With such an immense volume and diversity of data, how do we even begin to sort through all this effectively?
That's an astronomical amount of data, pun definitely intended there. I can only imagine the computing power required. This truly brings the universe to our doorsteps. But when you rely on something like citizen science for such crucial data, what are the biggest challenges? Ensuring data quality and consistency across potentially thousands of different people looking at it.
That's a really great question, and it speaks to the meticulous design behind these projects. Citizen science, in essence, is scientific work undertaken by the general public, usually guided by professional scientists. Its purpose is multifaceted. Volunteers help collect or classify vast amounts of data, which directly assists the scientific process. And at the same time, it helps to inform and educate the wider public about scientific endeavors. It's a win-win, really. Depending on the project, participants might collect and enter data, like observing bird or plant species, or, as in the case we're discussing, classify data, or even help train machine learning algorithms. The challenge of quality is met through careful project design, redundancy, so multiple people classify the same object, and expert review of tricky cases.
Okay, that makes sense. And a prominent example of this platform approach is Zooniverse, right? A massive web portal for citizen science. It has something like 2 million registered volunteers and hosts 25 space-related projects alone. Things like Galaxy Zoo, Gravity Spy, Planet Hunters, cloud spotting on Mars.
Exactly. Zooniverse is huge. And within Zooniverse, the project we're focusing on today is Gaia-Vari. It was specifically launched in June 2022. It's led by Christoph Nienertowick and Elsa Matthias, and it holds a special distinction. It is the very first citizen science project directly related to the Gaia mission data itself.
The first one for Gaia. So what's the tangible day-to-day task for a volunteer on Gaia-Vari? Are they looking for specific weird things, or is it more like broad pattern recognition? It sounds incredibly complex sifting through all that.
Well, for a volunteer, the task is actually quite specific and very visual. They're presented with light curves.
The brightness graphs.
Right, graphs showing a star's brightness over time for more than 10,000 sources from the DR3 data. This includes key types like eclipsing binaries, Cepheids, RLI-ray, and long-period variables. And these light curves are folded at the period determined by Gaia's automated analysis system. That means the graph basically compresses all the observed brightness changes into a single representative cycle.
Okay, so you see the repeating pattern.
Precisely. Volunteers, and as of the source material, there are already over 600 people participating.
600 already, wow.
Yeah. They visually inspect these folded graphs. They decide if the period the automated system found seems wrong, for instance. If an eclipsing binary shows two eclipses squished into one cycle, maybe meaning the automated system got the period off by a factor of 2. That's a common one. Or they might spot if the variability type itself seems to have been incorrectly assigned by the automated system. Maybe it looks more like a pulsating star than an eclipsing one, for example. And if we connect this to the bigger picture, this project isn't just about finding individual errors, though that's useful. It's about making the entire automated system smarter for the next big data release, DR4.
Ah, so it's like training the AI.
Exactly. Think of it like teaching an AI. You give it examples, you correct its mistakes, and it learns. This human touch, this subtle discernment, it fundamentally refines what the machines can achieve for the next data set, for DR4, which really raises an important question. What unique insights can human eyes bring that algorithms, even really sophisticated ones, currently miss? There's still something about human pattern recognition.
That's fascinating. Even though we can't show you the visuals here, the source material does discuss what these light curves look like for volunteers. So imagine a graph. The vertical axis represents the Gaia-G magnitude, which is the star's brightness. Brighter is usually lower numbers, fainter is higher. And the horizontal axis is the observation time, but it's folded at the inferred period.
Yeah.
So if a star has a period of 10 days, the graph shows what one typical 10-day cycle looks like based on all the data points.
Indeed. And the examples illustrated in the source material show 5 different variability classes: Acephi, Cepheid, eclipsing binaries, ellipsoidal variables, and RLI-ray. Each has a characteristic shape. For example, a perfect eclipsing binary might have 2 distinct dips in its light curve as one star passes in front of the other, maybe one deep, one shallow. If the period identified by the automated system is, say, half of what it should be, a human might immediately see that those two dips are being squished into what should be just one dip space on the graph, signaling an error in the period calculation. It's about recognizing those subtle patterns, or sometimes not so subtle patterns, that might elude even very sophisticated algorithms programmed with specific expectations.
So, what does this all really mean for you listening? It means even a subtle shift on a graph, something a human eye might intuitively pick up better than an algorithm. That could be a crucial clue about a star millions of light years away, helping to refine our entire understanding of the cosmos. It's pretty amazing. We've truly gone from a mere few 100,000 known variable stars to over 10 million identified by Gaia DR3, all thanks to a single, incredibly precise satellite. And what's truly remarkable is that citizen science is now the critical next step in refining that knowledge, proving that the human element is still indispensable, maybe more than ever.
It really is a unique synergy, isn't it? You've got this advanced space technology, cutting-edge machine learning, and then the invaluable, nuanced insights that, well, only human eyes seem to provide right now. This deep dive has hopefully given you a shortcut to understanding this incredible astronomical progress and, crucially, how you, yes, you, can actually be a part of it through something like Gaia-Vari.
It definitely puts it in perspective.
And maybe think about this, how projects like Gaia-Vari are not just about finding more stars, but fundamentally changing how science is done. What seemingly impossible scientific challenges could be solved next if we continue to empower millions of curious minds around the globe to contribute to research, literally from their homes? What's the next big problem we can crowdsource?